Welcome back to ECE 382. This is Kevin Byer here, working in data acquisition systems. So getting to those distance sensors on the front of your robot. We're going to learn how to use the analog to digital converter to take those analog sensors or signals from those distance sensors and convert those to a distance that means something to our robot and our controller. Start with kind of going through the theory of just kind of what's going on here, and then looking at how this applies to the lab. Specifically, how are we going to set up the analog to digital converters via the registers, and how are we going to sample and change that data to something that's meaningful, such as distance. So if we talk control systems in general, right, so we have the real world. Boom, real world. And we're going to have some kind of signal coming from that real world. So we have, for example, our distance sensors. We're going to send the IR infrared signal, and it's going to bounce back. That's going to give us a voltage between 0 and 3.3 volts. Now, depending on the sensor, that 0 to 3.3 volts is going to represent a different distance. So that's dependent on the sensor itself. But then we're going to take, the different circuits to interface with the microcontroller. So that's going to allow us then to potentially, you might have a filter in here of some sort. Just to smooth out that analog signal, because there will be noise. And then it's going to hit that analog to digital converter. We're going to do something with that data. So in our controller, we're going to process it. And depending on if there's a wall in front of us, maybe to the left or right, we're going to turn around. We're going to turn on some lights. We're going to do something. And that's where the actuation comes in. Dr. Beck's robotics course, 387, is going to go into a lot more detail and control systems with robotics, and then that's pretty much where you'll get your controls. And then we'll see control systems more in this course, specifically in Module 17, where we start taking all this data, and then from the line sensors, the bumps, and the distance sensors to do something in a maze, and that's going to be our control systems focus. All right, so 315, 215, whatever, ECE 215, 315, you saw analog to digital conversion. Basically, the basic concept, you have some kind of analog signal, you're going to sample it, and you're going to get some digital values out of that. That's the bare minimum concept there. We're not going to get all of the data, we're going to lose data, right? Because if we sampled all of the data, all of the values, that's going to take up a lot of memory. We don't have all that memory. Additionally, there's noise in these signals, so while, yeah, it would be nice if it looked like that, you might get some noise in here, and then if you're taking samples of everything, you're going to get some weird values that are going to really mess up. So some stuff to think about when we're thinking about these real-world systems: noise. And then how much space do we have to store this? Well, turns out we have about 14 bits. So we're going to talk about what that means later here in a second. We have 24 channels, so that means that we can, if we had 24 distance sensors, we could hook up 24 different sensors all around the robot and get 24 different angles of distances. And then we're going to, the analog to digital converter can take in about 1 million samples per second. So given that 2 to the 14 equals 16383, we know our voltage is between, it's a 3.3 volt source. And so that gives us this equation right here. It's going to give us our output in digital value. And then we're going to see later how that then will correlate to a distance with this specific distance sensor. All right, so let's go a little bit more detail into this analog to digital conversion. So the key three words here: range, precision, and resolution. So basically, range, so maximum minus minimum value, minimum. Too many consonants in that word. Value is 3.3 volts minus 0 volts, or 3.3 volts. All right, our precision is the number of values from which the amplitude of the digital signal is selected. So let's write that down. Number of values. And this is based off of the number of bits in our analog to digital converter. So for us, that's 2 to the 14, or 16384. So when we take our range now, which is 3.3 volts, we can look at the resolution, which is the smallest change. That is significant. And that's going to be our 3.3 volts divided by 16384. So that's, we take here to here, that's going to be our resolution. The number of lines here, that is our precision. And then from here up to here, that is our range. And basically, we take a look at the time on the x-axis. That's going to be our sampling rate. So say we're sampling here every second. We take a look at this value here and here, and we just take a look and see what value is it closer to. Is it closer to 16 or 17? All right, well then it's 16. So obviously digital, very just 1 or 0, but on or off. So, and that's the basic concept there for those. So the sampling rate, remember from 315 or 215, that the Nyquist theorem. Whoa, that's exciting. We're in a whole new page here. Going back to Module 14. That's crazy. All right. Computers are awesome sometimes. All right. If the signal is sampled, and this is based off the actual sensor, f of s, and then we can do a digital sample between 0 and 1/2 f of s. And that's to ensure aliasing and all those good things don't occur. And so for us, we're going to sample our digital ADC, I think 0.5 milliseconds. We'll see that later. All right. And then we're going to oversample. Basically, we're going to sample faster than we need to. And then we're going to average those values together. And so that kind of goes along in the the ADC is going to be going faster than we need it. That's going to be set up in the actual settings, and then we're going to sample it 1,000 times and then take the average of those 1,000 to get one basic point for our distance. And we do this to improve the signal to noise ratio. Our buffer is going to be 1,000. All right, so that's our kind of theory behind the analog to digital converter. We're going to get these analog voltages. We're going to sample them at a certain rate. And we're going to convert them at a certain rate, sampling rates based off of our ADC analog to digital converter. And then we're going to take that ADC and we're going to actually read values from it 1,000 times. And then we're going to average those together. So averaging together basically acts also as a helps us to kind of do like a low pass filter as well. So we can average through, and then once we get that value out, then we're going to display that and test that. All right, so that's kind of the theory behind it. I'm going to stop this video, start another one. The next video is going to be a little bit more lengthy, talking about the lab setup and what we need to do to get our analog to digital converter working correctly and get us set up to convert those analog values to digital, the digital readings then to an actual distance. See you in a bit.